Hello, here we are again. We're now at the conclusion of the mixer problem, and we're down where we have to do a tolerance stack. Now, we applied the tolerancing. That's the way that I would do it. I would make my best guess when I applied the tolerancing on the mixer or any parts. What I would do is make my best guess on what I have done before and past experience and kind of best judgment applying the tolerancing. Then after I applied the tolerancing, then to make sure that my numbers sound all right, what I would do is do a tolerance stack. And after I did the tolerance stack, I would look at the numbers and then come in and find out in the end how much all of those tolerances accumulate, right? What's the maximum misalignment that I could have? And if need be, I can reallocate my tolerances based maybe on process, based a little bit on, past experience, where I think the parts are going to come in, or capability of the process. All right, so let's take a look here now. Now, this here is our drawing, and this is the drawing of our mixer assembly. And this is how we should be thinking of this part. Remember when we initially started doing the tolerancing on this, we set up a datum reference frame on the housing. And that was kind of our global reference frame on this housing. And this is the way we thought of it, is this was our datum reference frame. We took the axis of the bearings, right? And then we said that it was the bottom part on the shaft, and that's the way we thought everything worked. Generally, that was the picture that we thought of. That's kind of the vision you had in your mind, and then everything else could be off from that. And that's really, so what I did is I drew a black line in here on the datum reference frame. Now on the datum reference frame, now this is the way you want to kind of think about it, right? As things moving, right? The shaft is always moving, is always there in the center, and all the other components are moving about that, right? So that's the way you want to imagine that thing. See how that thing, everything is moving? I say, oh my gosh. But that's really what's happening. It's just smaller tolerances, right, as they're moving around. So we're going to do a tolerance stack based on that, and then see where everything can be. So that should have been our thought process here. Now, in order to complete this tolerance stack, here is a drawing of our part. What we're interested in doing is calculating the mismatch between the coupling and the shaft. Want to find out what misalignment, all the tolerances that we had, what's the maximum misalignment that we could have, and this part still go together. So we're going to take a look at our drawing here, and what we have to do is to see what contributes to that. Now you notice that contributing factors here, that here's our shaft, here's our electric motor, right, there's coming in, and we're looking at that. So what we could do is very easily we could in the way we designed it, we designed everything on center, right? Everything was on center. We never went off the center, so everything was on center. So in theory, everything should be perfectly right on center. And I suppose if we took all the nuts and bolts and loosened everything up and pushed it around, we could get it to line up. But that may not be the case, right? When they're assembling this part, it could be where they assemble it sideways, all of the parts, gravity pulls them down, or some kind of automated assembly puts them together here. And so we could have some misalignment. And what we'd like to do is calculate worst case misalignment that we could have between the coupling and the shaft. So what causes that misalignment? Well, what I would do is let's take a look at this here very closely and take a look at the misalignment, things that would be contributors to cause misalignment. And what I would do is label those as joints, right? As joints. So we can do this really easy. Remember how we learned to do this in earlier lessons? That all we would do if we want to find out what that was, find out what the outer boundary of the coupling is, the inner boundary of the shaft. And then we could tell what the misalignment was over here, because when you're going to set that set screw in, it's going to push it to one side. So the difference between that boundary and the difference between the shaft boundary, the inner boundary on the shaft and the outer boundary of that hole, we could figure that real easy. We're going to do that in a second. But there's other contributing factors. And other contributing factors would be this joint right here. You see where that shaft goes into that bearing right there? That's going to be a contributing factor. And then number two, another one, and I'm labeling them. You would want to do this on your drawings too, or any kind of a stack that you would do, you would label them. And then the next one, what I have is where this bearing fits inside of the housing, right? Is there some kind of a joint here? Now, if it was a press fit, it probably wouldn't have any impact on us. I guess I shouldn't say that. It depends on what the position call out was and some other factors. But here I'd have another joint, right, where the bearing fits inside of the housing. And what I did is I labeled that joint number 2. Then I'm going to come up over here and you see where the adapter fits onto that housing. I look at that and I say, oh, that's another joint where it could cause misalignment. That's going to be joint number 3. And then I'm going to take a look up over here and you see where the electric motor fits into our adapter over here. That's going to be another joint. That's going to be number 4. And then I'm going to take a look over here. I'm going to find out from that shaft to that coupling, right? If there's any clearance between the size on this diameter and this one, that's going to also come into play. So when I'm going to do these, what I'm going to do is I'm going to always find the worst case outer boundary. So when I'm going to be looking at, for example, something like this motor shaft, I'm not only going to just take the size of the motor shaft, but you remember this is where my datum was. It's going to tell me how much that was off. And I think if I remember, what do we have, some 2,000th position on that. So if we did, well, I'm also going to take that into account, right? So it's going to take into position and everything else. And I'm going to go through, so that's why we're going to do inner and outer boundaries, not just the size of them, but the actual location of the features too. So for example, down here, remember on our adapter, this was the datum, and it said this diameter could be off within 2. So when we figure the outer boundary, we're going to figure the largest diameter that could ever be plus the position, right? And that's going to give you the worst case outer boundary where that can be. And then the motor goes in it. We're going to find out what its boundary is going to be, but it's not going to have a boundary because that was the datum, so it's just going to have size, so that size fits into that, and we're going to go down through. So we're going to have these 5 different joints that's going to contribute down here. So let's start that off. In the first place, what we're going to have is a tolerance stack form. It's going to look something like this, and this is doing it by way of the boundary stack. There is other stacks that you could do. You could do a vector stack. Vector stack, you would have vectors that would go back and forth. To me, they're a little more complicated. They're more difficult. These are easy for me to understand. I like doing these. These are my favorites. Now, this here is our stack form. And for those of you who have been in the earlier program, the stacks program, you remember in this initial column, in the first 2 columns right here, we're going to do the initial feature. The initial features that we're trying to figure out. And then in the next columns down here, we're going to put all of the joints to contribute and would cause that misalignment up here. So in this initial 2 over here, you see what we're going to do. We're going to come in and we're going to put the boundaries of these 2 features. Those are our 2 initial features. It's going to be that diameter, right, and it's going to be that shaft. So what we want to do is we want to find the outer boundary of this piece, and we want to find the inner boundary of this one. So let's go ahead and do that. Here's our shaft. I took the shaft, and what we want to do is we want to find out the inner boundary of this feature here. And the inner boundary of this one here, it's kind of small, so you might have your detailed drawings over here, and the inner boundary of the shaft is 434. And how I arrived at is I took the smallest diameter, which was 436, and the smallest diameter 436, and it has a position of 2. Now this is a regardless of feature size, right? It is a regardless of feature size modifier in it here. So if it has a regardless of feature size modifier in it, let me make that a little bigger so you can see that. So it has a regardless of feature size modifier, and if it does have that regardless of feature size modifier, then we have a formula for that, and that's in the stack program that we go through that. And rather than going into formulas here right now, if you have your stack book, you can remember what that formula is. Basically what it's going to be is it's we took the nominal size, which this case would be 437, and then we to find it out, we would subtract half the size tolerance, brings us down to 436, and then it would have taken us, subtract the geotol, and that would have given us that 434. So we have an IB of the shaft that's 434. Now we're going to take a look at the outer boundary of the coupling. And the outer boundary of the coupling, you see, is the largest diameter you could ever have would be 443, and then it could be off position within 5. If it could be off position within 5, that's going to give us a 448. So the difference between the inner and outer boundary of the initial features is going to be 14 thousandths. Now, what we're going to do is what I like to do is put all of this information in our stack table so we can all see it. So we're going to just record those numbers. You see the size of these different diameters are 443 to 439 and 438 to 436 in a geotol. We're going to enter that information inside of our table. And in that stack table in the first column down here, see, this is the coupling. And these are our initial 2 features. The coupling, this is the minimum of the coupling. Minimum size, that's the maximum size of the coupling. That's the geotol. And what it has is a regardless of feature size modifier. If it has a regardless of feature size modifier, we're going to use the S formula. There's a formula in there. In the stacks, there was 4 different formulas I showed you. We're going to use the S formula. And when we do that, that will give us, we'll calculate out the inner boundary and the outer boundary. So that's the inner and outer boundary of the coupling. On the shaft, we're going to do the same thing. This was the minimum size, that was the maximum size. It was an external feature. All right, the coupling was a hole, so that was an internal feature. And then we're going to use the regardless of feature size formula, and that's how we come up with the inner boundary and the outer boundary. Now the worst case, what would be the worst case that you would ever have? Once you have your data entered in the chart, well then you just kind of reason it out. You say, well, the worst case I would have is when I had the shaft, the worst case inner boundary, and the worst case outer boundary of the coupling, and the difference between those two numbers is 14 thousandths. So I have a misalignment there of 14 thousandths. Now what we're going to do next is we're going to go up to the assembly, and now we're going to take a look at all of our details and all of the joints. See, there's joint number 1, there's joint number 2, there's joint number 3, there's joint number 4, and that's joint number 5. We want to total up all of the misalignments, right, between all of those joints, and we did that just like we did the initial two features here. And then we're going to record that information. So that's what I want you to do is take that information and fill it in this chart. So I actually put it in here for you already, the bearing, the upper bearing, and then the shaft upper. And remember, we had two bearings there. It was really an A-B. What I did is the two bearings were equal in size and clearance, so I just used the upper bearing. That was the one closest where we're going to do the stack. Ideally, you would use both of them, but they're the same number, so we'll just use one of them. So they're going to have joint number 1. This is going to be joint number 2, joint 3, joint 4, and it was joint 5. And after you did it, you're going to find out what the maximum is of each one. You're going to total them up for the max, and that's going to give you your maximum mix alignment. And you're going to do the calculations down here in the evaluations and show me how you did them. So what I'd like to do is give you a little bit of time. You go ahead and do those problems. The inner and outer boundary formulas, you can find them in the stacks book. And then also, there's also some information on calculating inner and outer boundaries from the in the standard book, the fundamentals book that we have. You can have some information in there. So I'm going to give you some time to do those calculations, and then we're going to come back and see what the solution is. So we'll see you after this. Well, welcome back. We're going to take a look at the solution to the mixer problem. Remember, what we were going to do is do an analysis, a tolerance stack, and be able to calculate the misalignment between the axis of the shaft and the axis of the coupling. And if you remember, earlier in our book when we originally did the tolerancing, we had a goal there that we had to maintain that coupling couldn't withstand any more than a 40 thousandths misalignment. So we have to stay within that guideline, that max condition. So let's take a look at our problem here and see how we did. Now, where I left you, if you remember, this was our problem here. And this here is our shaft, and then we had the coupling. And when I would put that set screw in, what it's going to do is it's also going to cause a further misalignment. So we're looking for the maximum misalignment that I could have between the two. So remember what we did. In order to calculate that, first we had to determine what was our initial features that we were trying to calculate, and what it was is the shaft and then this diameter of the coupling, right? Those two are initial features. That's our goal. That's what we're trying to figure out. And I think that's what I helped you out in the beginning. We'll just go over a quick review on that here again. Now remember, this here is a little more of an advanced concept, and you should have had the stacks program earlier, and be familiar with some of the formulas and things we're going to do. All right, let's go on. What we did is we said that these two are initial features, and there were some joints that contributed to that total misalignment. And so if we could calculate what that distance, what that misalignment was over here, just from that feature to that feature, just in a static condition, all right, the worst case, then what we'll do is go take a look at the joints. Remember what the joints we had. We had this joint. That was number 1. We labeled that as a joint. We had joint number 2. Probably we did have some misalignment in the bearing also, but I didn't include that. That's just a purchased item, and we'll say that we're not going to include that into our calculations here. And then this here was our joint number 3. And then our joint number 4 was up here, and our joint number 5 was over here. And then all of those attribute to all of that misalignment there. All right, take a look at joint number 1. Okay, joint number 1. Let's see, what was joint number 1? Joint number 1 was the the relationship between the shaft and the bearing here. Now there's really two bearings, isn't there? We have a bearing here and we have a bearing here, and it was really both of them that did the misalignment. And I should factor in both of them, so let's take a look at both of them and see what kind of misalignment we have. And when I take a look at both of them, see, I put the bearing up over here. Now you have all of these drawings and things in your workbook, so they're probably not laid out as nice as I have them here, but you should be able to go through that pack of drawings and be able to find these numbers. Now this was our bearing diameter, and remember we were looking for this fit over here. So I took a look at the relationship between, let's take this one, this bearing, the top bearing, and then I took a look at this shaft diameter and then the hole here. And I took the OB of the bearing, the worst case outer boundary of the bearing, and the outer boundary of the bearing was 6253. That was the worst case outer boundary, and the worst case inner boundary of the shaft turns out to be 6249. And so I had a joint there of 4 thousandths. Now what I did is I also, remember, since both of them contribute, I took a look at the other one, the other bearing and joint, and we found out that that had a clearance there, or worst case there, of 4 thousandths also. So I'm just going to enter only the one bearing into the chart. And if I had one that was a little bit looser, well, then I would include that tolerance. But because this case, they're both the same, so I think all I need to do is add one. And I'm going to take the upper one because that's closer to the calculation that we're interested in doing. So we'll take that data and we'll enter it into our table. And you notice here I put the bearing, I put the minimum size, the maximum size, the geotol. This here was just size. Now we could just use the regardless of feature size formula for that. That told us what our outer boundary, inner boundary, and that was our 4 thousandths. So that joint gave us 4 thousandths. All right, next we have to go to joint number 2 and see what contribution that gave us. And let's see, joint number 2 was now the bearing, the outer diameter of the bearing, and the housing. See where it matches the housing? We call that a joint. We said that would contribute. So let's take a look at that joint, what that will give us. And this is what I have here again. Oh, we have the same thing where I have the A-B kind of an arrangement. And if I took a look at the outer boundary of the housing, we found out the outer boundary of the housing here was 1.6255, and then the inner boundary of the bearing was 1.6245. And I found out that joint number 2 here we calculated gave us a 1,000th joint. And we found out the lower bearing was the same thing. So I would feel comfortable in using just 1,000 because it was the same. Now remember, if you did have misalignment, probably what you'd have is you'd have some tilting on this bearing too, wouldn't you? Or one would tilt relative to the other from here. But within 1,000th and the distance there, we'll talk about tilt a little bit later when we get to that. So let's take that data and we'll enter that information inside of our chart. We're going to enter that in joint number 2. See, here's our joint number 2. And we said that the housing, that was an interior feature. There's an external and internal feature. And then the sizes, I put down the sizes so everybody could see it. And you could keep your work right, neat, so everybody can follow it. And there's our geotol was 0. There was no geotol, that was just size, but we could use the regardless of feature size form, and this was an inner and outer boundary, and we had a 1,000th at that joint. All right, now let's take a look at joint number 3. Joint number 3. And joint number 3, let's see, what that was is that was the relationship between the adapter and the housing. And now what we're going to do is find out what that joint was. And remember where our datums were. Our datums were right in the center here from that housing, and we came in and we positioned this housing. Remember that diameter? I think we had a position on it of 2 thousandths. Let's just take a look at the housing to make sure what we did give it. Yeah, that's what we did. Remember we had a position on here of 2 thousandths in relationship to A and B. So what we're going to do is figure the outer boundary of this. And the outer boundary, the worst case, or no, we're looking for the inner boundary on this one, aren't we? This here is the housing. So the inner boundary would be 2.748 minus the 2. That's where it gave us 2.746. And now we have to take the outer boundary of this adapter. And the outer boundary of the adapter was 2.753. So the difference we had between that was 7 thousandths. So we're going to take that information, we're going to enter it into the chart. So you notice when what we're doing is on the chart, we're not only just entering just the size of the housing here, but we're also including the position tolerance, right? That would be included in that, right? On this one, obviously, we didn't have any position tolerance because that was a datum. All right, let's go back and enter that data into our table, our stack table. And with the adapter, that was an interior feature. And this was the sizes. This was the geotol, was regardless of feature size. And this was our outer boundary. And in the housing, we were looking, that was an exterior feature. And we took the minimum and maximum, and then we figured the worst case inner boundary. Right, so we're looking at the inner boundary to housing, the outer boundary adapter. We had 7 thousandths there. So that's our joint. Now remember earlier, if you remember in the stacks program, and I think a little bit earlier also in the stacks program, and when we did the adapter, or not the adapter, but the optic connector, I showed you that there's a little Excel program that you can put the information. You can make one up yourself. It's pretty straightforward. Anybody has some experience with Excel. And you have the formulas that's in the stack, and you can go through this, and it's actually pretty simple. All right, let's take a look back here. So we had 7 thousandths on that joint. That was 3. Now let's take a look. Now we have to go to joint number 4. So let's travel over to joint number 4. And joint number 4, we had pre-labeled these. Remember, and if you're doing a stack, you want to label these so it's very clear. Now we have the electric motor and we have the adapter. Now this was a purchased electric motor, so we'd have to find out what kind of tolerance they're going to have on that. We didn't do anything with that, but this was our part that we had toleranced up. We'll take a look here, as we got to find out the worst case inner boundary of this motor. And the inner boundary of that motor here is going to be, well, the smallest diameter, 2.996. And that's it, right? Wouldn't get any smaller than 2.996. So that's the smallest diameter that we would have. There's no position on it. We don't have to include any of that, so that's really going to be size. And now this adapter here, where it goes in, we're going to have to take the worst case outer boundary. So the largest the hole could get is 3.002. But remember what we had is we had a position on there of 2. If we had a position on 2, that would give us what could happen. The hole could get larger, and then it could move over. And if it moved over, it could move over one way, one the other way. That's adding another 2. 3.002 plus the 2, that gave us the 3.004. That was the worst case outer boundary. And the difference between those would have given us a joint then of 8 thousandths. So let's enter that information on our table. And here we did that. There's the adapter, the min and max size of the adapter, the geotol, and then worst case calculation of the outer boundary. And then the motor, that was our purchase motor, the inner boundary, and that's where we got our 8 thousandths. Now remember, our goal here down at the end is that we wanted to make this thing a maximum of 40 thousandths. We couldn't have any more than 40 thousandths misalignment, so that's our target. And when you're looking at that initially, when you're initially putting the tolerances on, you can kind of look at all of the different joints you have, and you say, okay, I have 5 joints, I have 40 thousandths, so you got a rough idea how much to put on every joint. But sometimes size is involved and position is involved. So many times I'll put my tolerances down just like we did on ours, our best guess where we thought we were approximately, and then I go back and do a tolerance, and then we reallocate the tolerances. So it may be as we're going on, we can reallocate the tolerances. Looking back at our chart, you can see that the different joints we have. The initial feature we had, that gave us a 14 thousandths misalignment. The bearings were 4 thousandths. We had a 1 thousandths misalignment at this joint here. I think that was the bearings again, wasn't it? That was joint number 2. Now some of these are 7 and 8. So we might look back if we need to. All right, let's go on here. We're going on to joint number 5. Joint 5. Let's see where it is. Okay, that's the coupling. That's where the motor attaches to the coupling. And probably what's going to happen is when you take a set screw in here, that's certainly, it's going to push it to one side, isn't it? When you tighten up that set screw, it's going to push it to one side, so we'll certainly have that misalignment there. So let's take a look at what we'll have. And this here is, now on this motor, what we're also going to do is we're going to include the position on this, right? So let's see, what I would worry about here is the inner boundary. And the inner boundary on this, and then I'm going to take a look at this, and I'm going to take a look at the outer boundary, worst case outer boundary. So the inner boundary, well, let's do the outer boundary first. I usually do the outer boundary first, see, so then you can subtract real well. So the outer boundary on this one here would be 443, and you can see that number there, 443. That's the size of that, and you have all of this data inside your solutions there in the back, so you should be able to follow along. And I'm sure if you were working on this problem, you are familiar with these numbers here already. And then we take a look at the inner boundary of this motor, the shaft, and the inner boundary was 436. And then we also included a position, so it could be 436, and then it could be off-center too, couldn't it? So that would be 432. So the difference between that joint number 5, we have an 11 thousandths. So I'm going to take that data and I'm going to enter it into my chart. And when I enter it into my chart, this is the data, this is my tolerances, and you see I come up with my 11 thousandths joint. Now sometimes people say, well, do you need to add all of this? This here is it's just more of an administrative task, isn't it? You took all of that data and you took it from the drawings, and I just wrote it all out so you would be able to see it. If you were doing a formal stack, sometimes it's nice to have all of this here. Now you can come in and you can compare all your joints and see what's going on. So it looks like a total of our joints, and that's not including the initial feature, just our joints here. The total of the joints, if I total them all up, we now have, on a diameter, we have 0.0274. That's the total of all of our joints. And what I'll do is I'll take all of my joints now, and I'll say my initial feature, I had 14 thousandths. Remember, with worst case, just by itself, and I take the 14 thousandths, and I'm going to add the total of all of my joints. And the total of all of my joints was the 0.0274, and when I total it all up, on a diameter then, I have 0.0414. And on a radius, that would be 0.207. So we're a little bit past our target here, aren't we? We were supposed to stay within 40 thousandths. That coupling there, it had to stay within 40 thousandths. Now this is a worst case analysis. We could look at some statistics on this. We could look a little bit about the process. I'm not doing anything with statistics here, which could be added. In fact, you could do a stack table and add another column and do the statistics. I didn't do that. This here is just a worst case analysis, so it's very clear, and then you can add your statistics afterwards. So it looks like we're a little bit over. We're about, what, 1,500 or so over. So we have to go back then and reallocate our tolerances. So we had a pretty good guess initially. So that's what I would like you to do is if you're there with some manufacturing people or some quality or design, it's kind of a little bit of a design review here now. I want you to go back and take a look at where you're going to reallocate to make sure that we fell within that tolerance. Now, I want you to be aware that we're not done here yet. We did not consider tilt on this part. Let's just take a look at that, the tilt on this part. You see that we have some tilting to remember when we set the datums up on this part. We had remember this was our datums in the housing, and we had a perpendicularity on this face, and that could cause this housing or this top adapter to tilt. And then on top of it, remember on the top of that adapter we had some tolerance and could allow this to tilt. So we have to add that in yet. So we're not done yet. But the initial just, an axial back and forth, this is what we come up with. Is we come up with the total misalignment on a diameter of 0.414, and on a radius that was 0.207. So what I'd like you to do is take a look back at our stack table then. And I'd like you to go back and see where you're going to make some adjustments. Now, if I was going to make some adjustments, what would I do? Well, over here on the bearing, there's really not too much you can do there, right? That's the bearing. We got that out of the bearing catalog, but it's so tight here anyway, we can't really do anything there. This was here also where we were doing the bearing. See the housing in the bearing in the shaft here? So that was joint number 2. And we can always go back and look what joint that was. And probably some of the areas here we have 7 thousandths, the adapter and the housing, the adapter and the motor, the coupling. But it looks like we have initial features here. We had quite a bit here. So if I was going to look to readjust, it looks like that would be a place that I would look at first. Right? That seems to have, why is that joint so big when some of these other ones here are so tight? Now it could be that maybe it's a purchased even coupling that we already have, and there's nothing we can do about it. Well, then we have to readjust someplace else. Now you notice that when you're looking out here where the worst case was, what I'm going to do is now go back into the table and then see what I want to adjust. So I could readjust. I could adjust geotol. Here, for example, we have 4 thousandths. Now, why is that 4 thousandths and the rest of them are 2? Well, if you remember why that was 4, remember that was on the motor. That was the motor we were buying. That's what they gave us. So that's all we could, not too much we can do about that. But we can go back here and look at the size tolerances even, can't we? We have all of the feature sizes. Now we can come back and you see what we have in feature sizes here. We have 2 thousandths for feature size here. You know, we have 2,000 for feature size here. Here on the coupling, look at this feature size. See, from 443 to 449. Well, that's quite a bit of feature size tolerance. But you know, it may be a different material. That coupling, probably some rubber or hard, you know, some type of flexible material. So maybe we need that kind of tolerance. But you can see that how we're going to go about looking at it. Our modifiers here are all regardless of size. And you notice if we're trying to keep things on the center, that's probably what it would be. So nothing would change there. But if you're working with other cases where you have a maximum material condition modifier, you might take a look at rechanging some of those. You might take a look at least material. Now, least material, generally the stack won't change. You'll end up with the same end result. The only thing is you'll get a little bit extra tolerance, you know, as the feature departs. So if you remember earlier, I showed you some of the places where you could take a look at that. So we're going to end it here on this stack, and next I think we're going to take a look at the orientation stack. And the orientation stack on the mixer here will be next. So we'll see you there for the mixer orientation stack. Hello, welcome. We're back taking a look at that mixer, really beating that mixer to death, aren't we? Poor mixer. What we want to do now is take a look at the orientation problem we have with the mixer. Remember here a little while ago when we were looking at the stack problem we had with, let's take a look at our model here, and we take a look at our mixer. Remember what we did with just a linear stack. In the linear stack on this mixer, we had all of these different pieces that were going together. You see, here's our piece that went on, our adapter, and you see we had the coupling that was matching up with the shaft here. And all of the problems that we had, when the two went together, initially, what the initial calculations that we did, we were just trying to find out the initial calculations between this diameter here of our coupling and then the shaft when they went together. But remember what we did just a little while ago is we had a lot of contributing factors there. And the contributing factors is that, I guess we had the bearings, right? The bearings, how they fit on the shaft. And then we had the tolerance. We had another joint where the bearings fit inside of the housing. As you can hear that, they rattle around in there a little bit. And then after they went on, we had the adapter that went on, and it had a pilot, right? There was a pilot we had over here, and when the two went on, that rattled around a little bit. And then when we took the motor and we put it on, it had a diameter that fit inside of a pilot. And that moved around a little bit. So what we did is we added all of those together, and that's how we came up with that total misalignment that we have. So, you know, it's just pretty straightforward. Just add the joints. It makes sense, doesn't it? Just add all of the joints up and it'll tell you what the final is. Now, in this case here, we're going to look at orientation tolerances. Now, orientation tolerances could give us a little problem also. Remember on this part here, what we did is we had the datum. That was the axis. Remember the axis of the housing? And when we had the axis of the housing, that was our datum. That was our primary datum. I think we had a secondary datum, remember, that was inside where the shaft touched. And this top face over here, we gave a perpendicularity to, if you remember. And I think we had a perpendicularity on that within 5. Now, if that surface tilts within 5, it can tilt in all different directions within 5. You know what happens when we take the adapter, when we put it on top, right? Now the adapter tilts. And if the adapter tilts, well, you know what's happened. The motor is attached to the adapter, so what happens is that tilts there back and forth too. So as that tilts, that's going to give us some accumulation on tolerance also, cause some misalignment. Now, also what we had, another thing that we had to worry about was that on this adapter by itself, remember the datum on that was the bottom face, and then when we called off, I think on this adapter, didn't we? We said the face was the datum, and then this pilot was the datum, and we did that, remember, because that's how the part located to each other, and then that was our leaders, and then we told the followers how much they could follow along by. And when we did that, we came to that top face because we had to say something about that face. Remember, we gave it some height. We said up and down it wasn't too important. But the orientation on it, I think we put a parallelism on that face, and we had a parallelism on there within 5. Now, if you put a parallelism on within 5, well, you know what would happen is that face can tilt within 5. And when it tilts back and forth and in and out, you can see obviously when you take the motor and you put it on, if the motor's attached to that face, well then the motor tilts back and forth, doesn't it? And if it tilts, you see what can happen is this misalignment can cause over here, right? So what we would like to do is take into account how would we go about doing a stack on that. Well, I think it'll be pretty straightforward. This here is I think a pretty simple calculation that we can do, and I'll show you how we're going to do this. Now, we have done some of this in the stacks program, and we did it on the hub. If you remember, I had you do some stacks in there, and so we'd like to take a practical example on this mixer and show you how it would work. Now, some of you, if you're very interested in this, you might look at the stacks book. Otherwise, just kind of follow along and say, I don't want to know it that well, just general idea. How would you go about doing it? So let's take a look at this again. If this mixer went on, this adapter went on the housing, let's say do our first stack first, you see what it is it's basically a length, a ratio. And you see how high this is. Now you kind of have to imagine you're looking from this face into where that shaft is. And if you have a real big face and you have a short distance, tilting wise won't cause much of a problem. But the higher it is, right, the more tilt you're going to have. So we're going to have to take that into consideration when we do our orientation stack. All right, so let's take a look at our problem here. And you should have this in your book. And what I would like you to do is do this calculation. I'm interested in you to figure out the maximum misalignment that we could have. What will the orientation errors that have? Now, what I would do is I would label it here again. We have two joints. Remember our datum? Our datum was the axis here. Our datum on this part was the axis, and then I think we had a secondary datum that was here. So our shaft is standing up here like that. And I'm going to negate any of the tolerance on the bearings because we had, remember the tolerance on the bearings, the clearance on the bearings I think we had in there was one was 4/10, one was 1,000. So there wasn't much. I suppose we could add that in also, over that distance, what you could have. And you can maybe do that, take a look at that a little bit later. But bearings probably, if this is a rotating part, probably going to be on center. So I didn't include any of the tolerance in the bearings in this calculation. But on here then, this face, we allowed that face to tilt. And if we allowed that face to tilt, I saw that as a joint right there. And then I'm going to take a look at it. Remember on this adapter, that was the datum down here. And then we come up when we allowed that face to tilt. So what we have is we have two joints there. There's a joint there. That's joint number one. And this one here is joint number two. And this here is our stack table. And I have it all laid out. The formulas are right up here on top. So you can enter that data and be able to figure the worst case stack on here. So what I'm going to do is I'm going to give you some time to analyze this assembly and tell me what you come up with. I'd like you to do an analysis and calculate the worst case that orientation tolerances will have an effect on the coaxiality here. Because as that tilts, you can see that it will cause some tilt and total tilt error. I'd like you to calculate on a radius and then on a diameter. So I'm going to give you a few minutes based on your knowledge that you've had in the stack class earlier. This here is a practical example. It's an applications class. And see what you come up with. And then I'll come in and show you what I come up with. So we'll see you in a little while. All right, welcome back. We're going to take a look at the orientation stack on the mixer. And that is, I think you'll find this interesting. We'll see what you did, how you come up, and how you add it all up. And remember, it's just basically a ratio. And so let's take a look here what we have. Well, first of all, we had remember on this first joint, that was joint number one. On that joint number one, if you remember when we initially toleranced this part here, we had a datum reference frame. Remember the datum reference frame was in black, and on this top face, we said that face could move up and down within 10. Right? That's where we had our profile tolerance within 10. But then we said that also it could be off perpendicular within 5, and we allowed that face right there to tilt relative to the datum reference frame. And the datum reference frame is really where the shaft and the bearings and everything goes in. So if that's allowed to tilt, Took a look back at our detail over here. Watch our detail, what can happen. You see our tolerance down here? If this is your 5,000th perpendicularity here, and I greatly exaggerated that, but you see that if we're mounting on that face, see this length over here? See that distance over there and the height of how far this is? So how much can it tilt? Well, this here is where the end of the tip of the shaft is. And what we're going to do is find out maximum misalignment that would allow here, across here, how much that could tilt. And how much that could tilt off here, you know, from this point, it depends on how long that is. So if it's tilting here and it's tilting within 1,000ths, that maximum tilt would work something like this, you know, as it tilted back and forth. So what I'll do is this is our stack table here. And the way that it works here is this here is the, well, this is the geotol. First of all, what is it, the geotol that I have? And this here is a perpendicularity within 5. So I'll just enter that into my table, and I say that was 5,000ths. Now, the rest of this information in here, you know, we had the maximum feature distance and the minimum mount length. This is our formula, and the maximum feature distance divided by the minimum mount length will give us our contribution or our ratio. And remember how it works is that when you have a short distance over here and you have a long distance over here, if the shorter this distance is, the more that this will tilt out here. So what we're looking for is we're looking for that distance from here to here. And you notice what I did is I had a start point over here, and up here, when that motor is attached to the top of the adapter, how much it will tilt is kind of a combination of what that length is minus that motor length there. So I guess one of the first things we have to do is find out what the minimum mount length is. So the minimum mount length that I would have across here will be, well, let's see, it would be that adapter, and I have to take that adapter and find out the minimum diameter on that adapter. So let's do that. And here's the minimum mount on our adapter. And you notice on our adapter there I have a size that overall it's 4.750. Remember, that was the basic dimension we gave that diameter. And we had a profile on it. You see all intolerant surfaces were profiled on our title block within 20 thousandths. So that would give us an overall size then of plus or minus 20. And so minus 20, 4.750 minus the 20, that would give us 4.730. So the minimum mount length then would be 4.730. So we'll take that information, we'll enter it into our chart, 4.730. So now we know the minimum that we could ever have over here. Now we have to find the maximum distance that we could have over here, right? The minimum max feature distance. That's going, we're going to enter into this table here. So the maximum feature distance, what I would do is take that adapter and I would find out the maximum that that adapter could get. And then you notice that the motor, the shaft on the motor is attached to that. So then I'll find out what the minimum length of the motor, the shaft is. And then that will give us the worst condition, the furthest that can be away, because we want to do the worst case. So, and then we'll enter that into the table over here. So let's do that. What we want to do is we're going to take a look at this drawing now. We want to find the max that can get, and then the motor, the minimum that one can get. We'll do that. Let's see, the maximum the motor could get here is that we have this basic dimension, which is 3.750. And then we had our profile tolerance. The profile tolerance, remember, was 20 thousandths. That was our general profile. So if we total those things up, you would have 3.760. That's the maximum it could get. Now let's take a look at the motor. And the motor, the minimum that we could have on that motor would be 700. It has a 700 basic. Remember, it had a profile of 40 thousandths, all intolerant surfaces, so that would include that end of the shaft. So the smallest that could get would be 680. So we'll take those two numbers. And here was our 3.760. Remember, that was the maximum this could get, and the minimum this could get. We subtracted it out, and we come up with 3.080. So the maximum feature distance that you could have then would be 3.010. So you see what we have is we have a mount length that is 4.730, and then we have a feature distance that's 3.080. So now figure out what kind of ratio that's going to be. So we just divide the feature distance by the minimum mount length, and we'll come up with 0.6512 contribution, a ratio. Then we'll take that and that figure and we'll multiply it times our geotol. So we're not going to get the full effect of the geotol, are we? Because it's only a percentage of it. So if we multiply that out, we find out that in the end that what that does up here is it causes us a misalignment of 0.033 on a radius or 0.066 on a diameter. Now let's take a look at our model here and notice that when we figure it, why the amount here is double. You see, here's our part, and you see this was the face. We were on the axis. Remember, that was our datum. And you can see too, isn't it? You notice how important it is when you're selecting datums on the part. When you're selecting datums on the part, when you go back and you're going to do a tolerance stack afterwards, boy, just everything just falls right into place when it's done nice and correct. Makes you feel good afterwards. You notice how we nicely selected the axis of the datum, and then we had the faces, and we're going right through. So initially we did those calculations and we did them right, so now it makes our calculations here a lot easier, our stacks. Let's take a look at our model here again. And we had the axis. This was our datum to A dash B, and we said that that face could tilt. Now when it tilts, you see, and you take that electric motor and you put it on top, see what happens as it tilts? It tilts back and forth. And when it tilts, if it tilts this way, right, it could tilt this way, remember, within 5, but it could also tilt this way within 5. You notice what it's doing is it's tilting double that on a diameter, right, because it tilts back and forth. Because it could tilt this way, right, and it could go off, it could get off by 5, and it could also tilt this way within 5. So as it does that, then that's why we have double that amount on the diameter. All right, so this here is just a radius calculation, right? How much it could tilt one way, but it could tilt the other way, and that gave us on a diameter. So this here is our total tilt that we could have on this thing because of that 5,000 that we put down here. That's what it gives us up in the end. All right, now we have to look at the next one, and we're going to take a look at this joint number 2. So joint number 2 is the one that we're going to do next. Now this joint number 2, if you remember on our drawing, we took a look here, and that had a 5,000 perpendicularity on that. Now you kind of have a choice here. I'll leave it up to you. You saw how I did that one, and if for some reason you made a mistake in your problem when you did it, this would be a good time. If you like, you can turn me off. You can go and try and finish that problem and see if you can work it out yourself and see what solution you come up with, and then come back and turn me on, or you could just let me keep talking and I'm going to go to the second part of it here. So I'll leave that up to you if whatever you want to do. All right. So let me continue here on the solution on number 2. On this one here, we had that face right there. Remember the datum? That was the adapter. We had that face as the datum. And then I think we had that pilot as the secondary datum. Then we came up to that face and we said that that could be off. And it says here perpendicular, but I don't think that was a perpendicular zone, was it? I think that that zone was a parallel zone. Well, in fact, let's look on the drawing. I think it was a parallel zone, not perpendicularity. Take a look at it. And on our drawing, sure enough, remember here, that was a parallelism tolerance. We had a parallelism tolerance there of 5 thousandths. So if we had a parallelism tolerance of 5 thousandths then on that surface, now we have it located within 20, but the location doesn't really cause us a problem. It's the orientation tolerance, the parallelism. So let's take a look back at our drawing here. And this is our tolerance zone. And remember what this is our parallelism zone. And you see what could happen is the part could tilt like that. And if it does, you see we're looking for the distance between here and here, how much that could tilt. And what it does is it could tilt in this way if it tilts within 5, so it tilts this way. And then what it could also do is it could tilt the other way. And we're looking for that worst calculation. So in here, what I did is I put the geotol. The geotol was 5 thousandths. So I put that information right in there. That was the geotol. And now we're going to have to take a look at, let's see, what do we need next? Inside this table, what we're going to find out is the minimum mount length. Right, so the minimum, when that thing mounts on, what's the minimum you could have? And what I would do is I would take a look at the motor, right? Because even though this part is longer, the motor is the one that's going to cause the tilt. So I'll take a look at the minimum that motor could ever be, the minimum diameter it could be, right? So that's the minimum mount. So we'll take a look at the minimum mount. And the minimum mount that we could have here, it says that diameter could be 4.500. That's the maximum it could be. But then remember, we had a profile tolerance of 40 thousandths, and when it's on a diameter, remember it's plus or minus 40, so the smallest that diameter could be would be 4.460, and that's this diameter here. Probably it'd be more appropriate if dimension came on the bottom, but that's telling us that diameter. So we'll take it, add that information onto our stack table, and here it is the minimum amount is 4.460. Now we have to find the maximum distance that that thing can protrude. So we're finding out the maximum distance, right? The furthest it is away will give us the most amount of tilt. And the maximum, then, we'll take a look at this detail and find out what that maximum tilt is. And that here would be 700, and then it can be more within 20 thousandths. Remember, because we had a profile of 40, so that would allow it to be as large as 720. So let's take a look at our drawing here. 720, we entered that information in here. Now what we want to do is we want to find out what ratio that is. Well, you see, we won't have much of a ratio here. You see how big the mount is and how short the shaft is? I think we talked about that when we originally toleranced the part, didn't we? So if we look at this here, let's figure out what our ratio is, multiply that out, and we get 0.161. And we'll take that ratio amount, that percentage, and multiply it times our geotol, multiply it out, and we find out that that gives us 8 ten-thousandths on a radius. It gives us 0.0016 on a diameter. Now if we total these up, we find out that we get a total contribution then on a radius from those orientation tolerances of 4 thousandths and 1/10 on a radius, and on a diameter we get 8 thousandths and 2/10. Now if you remember, a while back we did the alignment study here where we calculated back and forth and axial, and we found out that this coupling, the max that coupling could take would be 40 thousandths. And I think when we did our alignment study here back and forth, the axial, we found out that we had a total stack up there of 0.414, so we had a little over 40 thousandths. Now we'd have to include this tolerance in here also, right, on a diameter. So now we're up around almost 50 thousandths here on misalignment. So if we're at 50 thousandths, now you have to go back and reallocate. And when you're going to reallocate, you might take a look at some of these perpendicularity tolerances. You know, that is it possible that we could tighten some of these down? Because, well, let's see, what does it do? It seems like joint number 2, the perpendicularity of 5, really didn't contribute much, right? We only got 1,000. But you notice this one here, we put down here. So this 5,000 contributed a lot more, right, to that misalignment. And you can see why, because it was a lot taller, right? You can see that right away. So you can keep that in mind when you're doing your tolerance, applying the tolerances later on, and see actually what that adds up. And it's kind of common sense looking at them, you know, kind of a rule of thumb. So that 5 thousandths there on a diameter gave us 6 thousandths. So it may be that if we were going to reallocate tolerances, you know, this is probably where I would go and tighten up the tolerance here on this one, right? That perpendicularity tolerance. Really can't do anything about the mount length or the distance, right? But we can with the tolerance. And then remember, we got to take this and combine it with the tolerance we did a little while ago, and then reallocate everything to make sure that we fell within the zone. All right, that really beat this mixer to death here. There is one other calculation that I would like you to do, and I don't have the solution here for you, but this would be a linear stack that, and I will have the solution in the back of the book. But another calculation that I would like you to do that is there, it's a linear stack. I haven't done too much in the way of linear stacks, but I would like to find here between these two, between this one and this one, between that shaft and this shaft, what I'm looking for is I'm looking for the min and the max. And so that will be, you know, the min, and I'm looking for the maximum distance there. And I'll let you go through that yourself. You're going to have to start with the stack path, and you know, start probably at the top of the shaft, right? Because that's going to be, well, we'll start. This will be your start. This will be your finish, and go through all of the pieces. I'm not going to tell you where to go. I'm just going to let you do that yourself, and I'm going to see if you can figure out that min and max. And I'll have the solution in the back of the book, and then you can go through it, and then you can take a look at my stack table. You know, once we have the stack table, you can see what where I added and where I didn't add, and if there's any discrepancy in your answer, then we can compare. All right, I hope you enjoyed the mixer. That was kind of an interesting one. There was a lot involved there.